Hey folks, sorry I can't be there with you today, so we will do notes in the form of video notes instead of me at the board. What I'm going to be doing is pausing frequently, so I'm not making this super long. I can just type and draw things while I'm paused. We're here to talk about waves, and I want to take some time to sort of sum up all of the things we've learned, the key terms, the variables, the units, all of that, and what we learned from the lab. So we're going to start with a definition of waves that is right here. We say waves are a way of transporting energy from one place to another. It's not carrying physical stuff, it's carrying the energy. And that's being propagated through the medium, that's what the wave is traveling through, by vibrations in that medium. Which is what we saw. Maybe it didn't look like vibrations to you, but bits of slinky moving back and forth. And the nature of these vibrations is what's going to determine the type of wave that we're dealing with, whether it's transverse or longitudinal. So the different types of waves, longitudinal and transverse, we have, where'd my definition go? There it is. Transverse waves are happening when the vibrations of the medium are perpendicular to the direction of wave travel. That is similar to what we saw in the slinky. And if I draw that to represent what we're used to seeing, I've got my dotted line, which I'm going to call the equilibrium point. This is where the slinky was before we started moving it. So you can think of that as the slinky's laying along this line. And as we start shaking it, we get a pattern like this. Not a great sine wave, but it'll do. So we can't see this moving here, but on the screen, of course, but remember these waves or wave pulses could travel the length of slinky, like in this direction. That was a lousy straight line. In this direction, or the other one. Let's assume it's moving to the right. So that's the direction of wave travel. But the vibrations are this way, perpendicular to it. That's a transverse wave. Those are going to exist in solids, some liquids, not very well, never in gas. So there's a pretty good reason for that. If you look sort of at how the wave is being carried through the slinky, you start by dragging the slinky up here with your hand, and you're taking the slinky with it. So it pulls the next bit of slinky with that, and that pulls the next bit, and so on. And then we also should be thinking about, well, how did the things get back? Like if I'm whipping the slinky this way, and there's little bits of slinky moving in the direction that's up the screen here. Newton's first law says it wants to keep going. Objects in motion stay in motion. So what is bringing it back to the equilibrium point, back to here, is that it's attached to the slinky. So part of the slinky started getting pulled back, and it brings more with it. That only works because particles in a solid are attached to each other. That's why this doesn't work in a gas. Liquids, more or less, they can work, but it depends on how cohesive that liquid is, like if the molecules have a tendency to stick together. And you're probably thinking, yeah, but water waves, like we get really good waves out of that. There's also gravity involved in that, and it's kind of like a special case. So we only get these mainly in solids, some liquids. Not so much in liquid, never in gas. You don't have a transverse wave in air. This, incidentally, is how we figured out the core of Earth has sort of a liquid element to it, because the transverse seismic waves wouldn't pass through that, and we'd always observe a shadow of those waves. All right, next is longitudinal waves. So I started to draw a spring and try to do a longitudinal wave, and it was so bad that I found a picture online, and this looks way better. The longitudinal wave, same idea, except the vibrations are perpendicular now. So this comes already equipped with the direction of the wave travel in the axis of the spring. But what's going to happen is the vibrations are in that same axis, which is parallel to the direction of wave travel. Now these can exist in solids, liquid, or gases. This is the type of wave you're going to have, liquids, type of waves you're going to have for like a sound wave traveling through air, because the molecules aren't attached to each other. They can't pull each other back into that equilibrium position the way a spring does. So that's what we get for sound waves. In our wavy homework, we had looked up a bunch of different terms and symbols and units and all of that, and we should probably go through that to make sure that we're all clear on all these things. We had started with period, and the first day, actually, we did that one. The symbol for that is capital T. That's a measure of time, so the unit is seconds. The symbol for seconds is a lowercase s. I commonly write it as SEC because my s's often look like fives and mistakes have been made. We could define this as the duration of one complete wave in time, right? That's what duration would be. One complete wave. Very similar to that is frequency. Symbol is lowercase f. And the unit for that, well, there's several units. Waves per second is the most descriptive and useful one. It tells you what it means. It's how many waves there are every second. Makes perfect sense. Mathematically, waves is not really a unit. So it's technically 1 over seconds. So that could be, oh, I'm sorry, I'm writing this wrong. I should say waves per second. Spelling out what it is, that's waves per second here. Or 1 over seconds is actual definition. This is also called hertz, abbreviated HZ, which is just named for some dead guy. So I prefer waves per second. It's more descriptive. This would be the number of waves that are being created every second. Or maybe the number of waves passing you every second if you're sitting there watching them go by. Number of waves created each second. Okay, you're probably sitting there watching this and thinking, should I write any of this down? It's all right here. I don't have room for everything on here. So I'll be talking a little bit. Jot these things down. Right? Yeah, I could make the room, but part of this has to be you interacting. So these are things we looked at in our lab, trying to figure out what determines these. The things that we could change were the way we made the wave, that's the source of the wave, or the medium itself. The only two things we could really change about how we made the wave was how much we moved our hand in terms of amplitude and how frequently we moved it. That's it. Those are the only two things. So we discovered in the lab that both of these are determined by how you make the wave. If you want a 2 hertz wave, you move your hand at 2 hertz, and that creates a wave with the same specs. The same is true of amplitude, which is kind of like the bigness of the wave. That's a capital A. It's measured in meters, which is a lowercase m. And that would be, well, how big the wave is, but if I want to be much more clear and specific, the maximum displacement, that's just movement, of the medium, that's the stuff the wave is moving through, maximum displacement of the medium from the equilibrium point. I'm just going to spell equilibrium point EQ point. It makes sense to measure it from there because that's where it was at rest if the wave didn't come along. But that also kind of reminds us that we need to measure it from that center line. It's not from like a crest to a trough, it's from the crest to the center line. And that is also determined by how you make the waves. Another one we worked with was wavelength. Definition on that is pretty easy. It's the length of a wave. But that's not the length in time, that's physical length. Length of one complete repetition of the pattern. That's what a wave is. Repetition of the pattern. right. Okay, wavelength is this weird symbol, lambda. It's a Greek letter. It corresponds to an L for length. Makes sense. This is also meters and measures M. And if you look back at your lab, which hopefully you've turned in by now, so you can't look at it at this minute. But anyway, if you look back at it, you would see, how did we change the wavelength? If you were successful at that, it was from changing the period. That was the only thing that did it. So all these things, the amounts are determined by the source of the wave. Not anything else like the material it's moving through, just the source. In the case of the slinky, that was your hand. So whatever your hand is doing, the wave is going to do. So finally we got to part 4 of the lab, and part 3, and we're trying to look at speed of the wave. Speed is basically how fast something travels from one location to another. All right, symbol for that is actually a V for velocity. They're different. We'll get to that later. Just accept it as being V for now. And the unit for speed, think of like miles per hour in a car. Well, it's a distance per a unit time, and per means divide. So it's a length over time. And if we use our standard units, that's going to be meters per second, written thusly. So we looked at what affects this. Sorry about the dog. Sorry about that. My dog is adding commentary to the video as another dog brazenly walks by outside. So we tried to see what can affect the speed. We tried making a bigger amplitude, and that didn't do it. We know what that does. If you use a bigger amplitude on your hand, you're going to get a bigger amplitude wave. It doesn't change the speed. And the last thing we did is we tried changing the slinky itself. And that was the only thing that caused a change. So in the slinky, speed was determined by properties of the slinky itself. Had nothing to do with how you made the wave. So what we found, unlike all of those other parameters, this is the one that's determined solely by the medium. There's nothing you can do about how you make the wave that will affect how fast it travels. That's just a function of the medium the wave is traveling through. And in the case of a slinky, it would be like the tension. More tension means more speed. That's a direct relationship. In the case of sound waves traveling through air, temperature is a bigger factor. It depends on what kind of wave we're talking about, but it's always properties of the medium. Now, when we wanted to calculate speed, it's a very simple equation. Let's make this some room here. And the equation we were using was basically speed equals distance over time, or V equals D over T. Very simple equation. This dates back to middle school. You probably remember it. But it's worth mentioning, of course, this is a distance in meters. T is time. This is going to give you an average velocity by definition. That's all it can do. If I'm changing speeds the whole time I'm walking some distance, but all I record is the total distance in time, it's going to give me one value for the speed. It's just going to be an average. We can use this basically when speed is constant. Now that will be fine. The problems we're dealing with on working with waves, we're not going to be changing medium typically, so we're not going to be changing speed. So this equation will work perfectly fine. It's later on in the year when we remember this and try to use this when the speed is not constant that we'll run into trouble. But this is going to get us a lot of the solutions we're looking for the basic problems we're dealing with right now. Well, that's all I have for you today, folks. What I'd like to do now, review the notes if you need to. You can always go back and look at it again. We have a problem set, which the sub will be given to you. I want you to do your best to answer all those questions as best we can. Good luck. See you tomorrow.